All right. Hope everyone's having a lovely Wednesday so far. My name is Bishan Yakon. I'm the technical account manager for some of the aerospace companies for Altair, including Lockheed, Gulfstream, Textron, Safran. Yeah, today I'm going to show you guys the workflow for specifically for model building, or basically pre-processing for composite parts in HyperMesh. So I could spend, I could talk to you guys for hours about all of our pre-processing, post-processing, optimization methods. But we don't have all that much time today, so I want to mostly focus this demo on model building for composite models, specifically within the Nastran and OptiStruct interface. But a lot of these capabilities translate, pretty intuitively across the other, ANSYS or Abacus interfaces. I'll allude to some future capabilities that we got coming soon that I'm excited for. And I'll also allude to some of our composite optimization capabilities. But, again, we don't really have a ton of time to get too into the weeds on all of that. If by the end of the demo, if you'd like to explore any aspect of composite modeling or optimization capabilities within HyperMesh, just let me know. And I'll put the link to the chat to our survey where you guys can recommend or suggest future demo topics for us to cover for you guys. All right, with that spiel, let's get into it. And actually, before I get into HyperMesh, I want to discuss something real briefly here, which is the zone versus ply-based modeling approach for composites. So traditionally, composites have generally been modeled in this what we call zone-based approach, right, where you would define your ply stack up for the specific zones that would have these unique ply stack ups, right? So in this scenario, you might have 3 zones, but you might have some plies that carry over between these zones, right? So um, we believe that it causes, or in some scenarios, it might be, it might make sense, but that in many scenarios, this can cause challenges for visualization of the plies. And you got to often, like in this case, create ply 1 3 times or define ply 1 3 times for those 3 different zones. So what I'm going to mostly spend time on today is the ply-based modeling approach that we've taken in HyperMesh, where you can, instead of defining, these unique ply stack-ups per zone, you can just define unique ply stack-ups that are assigned to shapes or basically sets of elements. And so this gives you some advantages, like you don't have to, define a specific ply multiple times for each of the zones. You can just define it once and then specify what area of the mesh that ply will come across or will go across. And there's also some other benefits with better visualization of the plies within HyperMesh that I'll show you guys. So HyperMesh supports seamless integration or conversion back and forth between the ply-based and the zone-based modeling approach. So we often encourage our users to, if they have their data set from whatever CATIA or FiberSim or spreadsheet, we recommend modeling in HyperMesh using the ply-based approach. And then if needed, if you need to send it to a solver, like maybe Nastran, that doesn't solve directly on the ply-based approach, you can just convert your ply-based composite model back to a zone-based. So I'll show you guys all that and a little bit more. So let's jump into it. Okay. So I got HyperMesh here. I got this hat model loaded. I already have a mesh ready to go. So I want to first, just show you guys how to create just from scratch a few plies within HyperMesh or create a laminate within HyperMesh. But I'll really spend more time talking about the different import options between importing a CATIA model, FiberSim model, and importing a spreadsheet to define your composite layups. All right, so bear with me here. I got some stuff on my screen I need to move out of the way real quick. Let's move that down there. I guess I can't move that window. Oh, no, I can't. Okay, let's move that maybe over here. Okay, so we will go to the model ribbon up here and we'll open up our composites browser. If you ever forget where this is, you can always just come over to the magnifying glass and just search composites and it'll take you there. So the composite browser will give us all of our tools and capabilities for building out and analyzing our composite structure. So we'll come over here. Clearly, I don't have any composites in my model quite yet. So what I can do, maybe let me see. Yeah. So what I can do is just right click. And again, this gives you all of your options for creating, analyzing, querying your composites, etc. So what I can do is create a laminate. Okay. And then within the laminate, I can right click and create a ply. So I'll create my dummy ply first, maybe. Ply 1, thickness 1, orientation, maybe we'll start with 0. And then I can, there's some other capabilities in there, some other options, like what ply type. So you can also do like a core ply type, wound or weave. And then I'll allude to it or maybe touch on it a little more later, but we do also have a material, or excuse me, multi-scale modeling, multi-scale designer tool that can do like more advanced types of plies and composites. But yeah, for now, we'll just stick with a basic unidirectional, and maybe I'll just create not too many, but maybe we'll just do like 3 duplicates of that ply. All right, and then I can come and adjust, set my orientations for those. So again, if you're dealing with like 100 plies, right, this isn't going to be a particularly efficient workflow. But just to show you guys the options you have for just manually creating plies within HyperMesh. Okay, so I created a bunch of plies, and if I go to the model browser, I can like auto color them. Let me see, they'll be under plies. I often do this. I'll right click, auto color. So that'll make it easy to visualize the plies, which I'll show in a second. So, so of course we got to create our property for the composite. So we'll right click, create. So this is slightly different like card creation menu in version 25.1, but here I like you can search for card image. So I can say p-comp. And so you can create a p-comp-g. So this would be your zone-based approach where you can define your plies within a table for a specific zone. But here I'll use p-comp, which will give us our ply-based modeling definition. Okay. And so I'll specify my offset as 0. What this will mean is that it'll stack the plies from index 1 upward, starting from my mesh surface, basically acting as my tool surface, stacking in the direction of the element normals. Okay. So I'll go ahead and right click and assign that property to my components that or my existing mesh component. Right. And assuming I defined everything properly there, I should be able to visualize the overall thickness of that laminate. But I think I might be missing something here. Yes, I'm missing the shape. So the shape, that's an important element. That's basically the equivalent of the zone. So that's the areas of our mesh where we're generating these plies onto. So generally we would recommend creating sets for each of the distinct shapes, but in this example, I want to keep it a little simple. So I can just click on this dropdown and grab or assign these plies directly to the elements. And again, just keeping this simple, I'm just going to assign this Control A to select all of my displayed elements, and I'm going to assign them there. Now, if we zoom in, there we go. Now I can visualize this is the overall thickness of that composite laminate that I've assigned to my mesh through the p-comp. But now there's another option. We come down here to these visualization tools, this little like ply icon. This little ply icon will allow you to visualize the individual plies. We click on that. And maybe it's easier if I turn off geometry. Let me turn off geometry. There we go. So yeah, now I can visualize based on the coloring, right? So that's why I did the auto coloring of the plies. And so now I can even like select individual plies in the GUI and then adjust their thicknesses or orientations or whatever in the browser in the entity editor. So it's all connected there. So again, this is what we think is one of the big benefits of the ply-based modeling approach. Okay, and so of course there's some other things you got to check with defining your composite model. So of course one of them being um, that element normals. So right, I mentioned I did a zero offset for the P comp, right? So again, that's going to stack the plies starting from index 1, 2, 3, 4, etc. in the element normal direction. So we can check that if we go to D and review orientation. Go to the orientation tab, and then first option, display normals. So we'll grab all of our elements, Control A. It's a little slow today. And then apply. So that shows, of course, element normal stacking like away from the hat, but maybe in this case, I want to stack the plies down the other direction. So what I can do is flip this drop down and say reverse normals. Apply. Let me see. Let's make sure that it flips the element normals. I'll do another review. Apologies. I'm normally slow. I think it's WebEx slowing things down. Come on. Let's try that one more time. Maybe I'll do a box selection. That often works better. There we go. Okay, now we're stacking our plies inward. Right. So now if I visualize that ply stack up again, they'll stack downward. Out of the way. Okay. A few other things I wanted to show. So this is just a manual approach, and then again, if I wanted to export this model as a zone-based model, what I can just do is right-click on my laminate. So right-click and then realize the laminate. Okay, and then I can include drape. In this case, I won't. I'll say delete my ply-based entities, and then realize. Realization complete. You'll see it'll create a pcomp G card. In this case, just one because I only used one shape. But if you go down here, you'll be able to see your table with your plies that you created. So in our opinion, there's really no incentive against using the ply-based modeling approach, since you can just do a conversion with a couple clicks there. And then if you wanted to convert that back, let me see. What you can do is absorb, right-click absorb zone properties. So this will take you from a zone-based to a ply-based approach. That pcomp G, so you'll just select your pcomp Gs that you want to absorb into pcomps. Say OK, and then we're back. So very nice, very easy in my opinion. So again, this is just a more manual approach for defining your plies. What you can also do is import your plies via a bunch of different methods. So one method is importing a FiberSim file. So I got this FiberSim file. So typically this will just like define the stack up and the shapes. So what you would do is, bring in your CAD, mesh your parts. So like I have here, and then you can import. And let me, yeah. So what you can do is import a FiberSim F5 file as geometry to bring in basically like a drape table that you can realize onto your mesh. So if I drag and drop that, since it's an H5 file, it thinks it's a results file, but you would just go and change that to geometry and merge it into your current model. Okay, I'm not going to go too crazy with the settings here, but you'll see there it brings in all of my plies. But if we expand this a little bit here, you notice it's it hasn't projected or assigned those plies to my model yet. But what it does do is it brings in a table that that can make those assignments for us. So all we have to do is just realize these tables here. So if we go back to our composite browser and select all of our plies, you can right click. What do I want? I want realize. Wonderful. Okay, and then you would just click on this drop down to specify what kind of realization projection you're doing. So in this case, we're using a FiberSim drape map. We'll just select our component that we're going to realize that draped map onto, and then realize. You'll see it automatically creates some ply sets for us. So if we visualize, we should be able to see our plies here. I think, oh, yes, we just need to create the P-comp in this case. Or you could create a P-comp G here if you want to just model within the zone-based modeling approach, but we'll create a P-comp. And then assign that to our mesh. Yep. Nope, don't want to do another. Yeah, okay. So we should, there we go. Okay, just had to update the, let me turn off geometry, make that a little easier. You can see our stack up. And I should also say there's a few other aspects to the composite modeling capabilities that I want to show a little bit. So you can also right click to do various material and ply orientations, or reviewing ply orientations. So of course, like defining a material system can be pretty important. So you can right click material reference orientation, and you got all these options for, assigning through a vector, through a system, specific system axis. So what we would do here is define all of our elements, and we're gonna map their material systems to this system here, and apply. So you see there that sets that material reference, which you can always go back and query with the orient material reference review. So you can always check that out later on. And then if you want to query the fiber directions of the plies in the GUI, you can do that as well. So you can select one ply, doesn't matter where it is in the stack. You can just right click, review orientations, ply one direction. And there it's telling us that fiber direction. So you can just kind of flip through the plies and see each of their fiber orientations. Okay. Boop. Okay, so yeah, so that's the FiberSim approach. So there's a few other options you have for bringing in or for defining your composite model. Another one, let me go ahead, start a new model. So another one is, of course, you can just bring in a CATIA model that has the composites defined within it. So if I drag and drop this CATIA model, sure, it's a new model, geometry, okay. And so what you want to make sure that you specify if you're bringing in some CATIA model with composite data is you got to go to the entities tab down here and check off composites, right? Make sure you have this checked. We'll go ahead and open that. And you'll see it'll bring in the CAD, but it'll also bring in the definition of the plies that we can see within our composite browser. And so basically, we just got to do the similar process that we did with the FiberSim files, where you just generate your mesh, assign your P-comp, and then realize those plies onto your elements. I think I'm having some slowdowns with my internet. My apologies, folks. Okay, let me just, this might be frozen. Let me try just opening up a new model. My apologies for the internet slowdowns, folks. I'm not in my normal abode here. Okay, let's start up a new session. I think the other window, no, it's still loading. Okay, let's try dragging our CATIA model into here. Drag and drop. Okay, again, make sure we check off our composites and we'll open. There we go. Okay. So we'll just reopen our composite browser to take a look. So you see it brought in our laminate and our stack up. And with CATIA, typically defines the shapes by lines. So again, similar process, but we just got to generate our mesh real quick first. We just do a 2.5 element size here. Okay. Let me turn on this. And we'll create our pcomp. Oh, and you can also create your properties from here as well. So create property pcomp. And then we will assign, right click, assign that to our meshed component. Okay. And so again, we will just realize by selecting our plies, right click, realize, and then you can use the default method or the CATIA Composites drape method. And realize. Realization completed. Wonderful. And now we should be able to, assuming I did not forget anything, oops, should be able to visualize those thicknesses and the ply stack-ups there. So pretty easy, right? Just make sure you check off that composites checkbox. And then again, right, if I wanted to realize these into zone-based cards, I can just select the plies themselves. And then, oh, no, excuse me. You would select the laminate. So if you want to realize a laminate into zone-based cards, you right-click on the laminate and realize. Oh no. Oh, that was the other window. Okay. Okay. So that covers importing a CATIA model. There's another approach that you can take where you just use a CSV file. So let me bring in this model. I'll try to show this one real quick because there are a few other things that I want to just briefly mention here. So, okay, we have our laminate. So what we'll do, we'll create a laminate. Okay. And then we can just right click on that laminate and import a spreadsheet. So let me first show you guys the formatting real quick. Here we go. Okay, so here's your typical laminate spreadsheet format, right? You got your names, ply IDs, etc. Everything's, I think, pretty intuitive here, except for the ESID. So this is denoting what shape IDs that it's going to map these plies onto. So this is just based on the IDs of the sets you have in your HyperMesh model. So what I will do, copy that path. Again, right click, import spreadsheet. Okay. And then right off the bat, it maps based on those ESIDs, those element set IDs. It maps the shapes of those plies onto these pre-existing sets that I already had defined in my model. Right. Oh, yeah, and I would, again, also just have to create and assign that peak. But hopefully you guys get the idea so far. So I'll skip that step since we're running out of time, because there are a few other things I wanted to mention. One of them being, well, I guess I'll just assign this real quick. But we got some other capabilities. One of the really helpful ones is being able to view engineering constants using what we call the composite stress toolbox. Let me just assign that real quick. Okay, so just making sure I have my laminate properly defined. Hey folks, this is Bijan post demo, just coming in to fill back in and finish up covering some of the topics that I either didn't quite have time to get to during the live demo or was having some troubles getting to work during the live demo. Just some issues with my machine. But yes, one of the things that I wanted to make sure that I touched on was the tools, the functionality in the composite stress toolbox. So if you right click on any laminate or ply, what you can do is you can go right click, analyze, engineering constants. Okay. And what this will give us is our ABC, or excuse me, our ABD matrices. And then scroll down, our engineering constants, thermal expansion coefficients, homogenized matrices, and plane shear, etc., etc. Right? All this helpful information about all of our stiffnesses for our plies, or in this case, our entire laminate. Okay, and all this information can just be easily copied and pasted into an Excel spreadsheet. So you can just right-click anywhere here, copy, bring up an Excel spreadsheet, and then just paste. So Control V, paste, and then you can use the text to columns just using a semicolon delimiter. There you go. Now you got all this information, your ABD matrices, and all your engineering constants that you can send to your report. Okay, so again, you can look at that in terms of the overall laminate or even on a ply-by-ply basis. You can right-click on a specific ply, analyze, engineering constants for that ply. And then you can also look at, if you come down here, the plot. So for example, you can see the stiffness in the X for that ply material as it goes across that orientation range. So pretty cool. All stuff you can export to an Excel file very easily. So again, that's the composite stress toolbox functionality. In addition to the engineering constants, you can also use this toolbox to view load responses, first ply failure, and strength analyses of your plies. So you can also right click and create an analysis where you can define some of those other things. Okay, so that's the composite stress toolbox. You guys also have functionality for simulating kinematic drape. So basically simulating the stretching and warping of the plies as they get laid out across the shape, and the stretching of the fibers and thicknesses in the plies as they get laid out across the tool. Okay, so we can right click on our laminate, and again, you can do this on a laminate or a ply basis, and say drape, kinematic drape. Okay. So in the first tab, will give us our options for how we want to define how these plies are laid over the tool. And so you got a few options for quadrants, which would just be like basically defining a seed point, an initial point to lay the ply down onto. And then with the quadrants option, it would simulate sort of laying down that ply uniformly, like kind of like a rock hitting a pond, uniformly across the length and widths. Or you can do a linear draping method where it would be more so, basing on the seed point, draping the or laying the ply across the tool linearly initially, and then sort of projecting and laying out the ply laterally. And so when you open up the advanced options, you can sort of see those different options used for the quadrants or the linear method. In this case, I'll do a linear method, and I'll just grab a seed point, maybe right here. And whenever I hit apply, it'll create some drape tables, one table per each ply that gets automatically assigned to the ply. Okay. So if we look at any of our plies, we'll see now we have this drape table assigned. So you can view those new drape fiber orientations and thicknesses of the plies. If we go back to Kinematic Drape and then look at review, so we can see draping mesh, shear, flat pattern. You can see draping mesh, flat pattern. So this is basically like the shape of the ply before it gets laid out. Thickness scaling factor. And then your shear. So you got that functionality as well, simulating kinematic drape. And then one last thing I wanted to touch on, and I think this diagram gives a better understanding sort of those axis directions. And yeah, one other thing I wanted to mention was composite optimization that you guys also have access to. So we have a developed composite optimization methodology that you guys can employ. Generally starting with a concept level optimization, optimizing the ply shapes. So, what kind of ply stacking shapes are you going to use? And typically this and really all aspects of composite optimization do take some interpretation and some engineering judgment. Of course, not all of these raw shapes will be manufacturable. So it takes some interpretation that you can then segue into a composite size optimization and then into a stacking optimization. Okay. And just FYI, you do also technically have capability to optimize the fiber orientations themselves directly with OptiStruct. However, we typically recommend against this approach as because of this sinusoidal relationship between the fiber orientations and the stiffness of your plies. Often you just end up trying to like find a global minimum among a sine wave, right? So oftentimes that's not really very doable. So we in situations where you want to get a better idea of some of the optimal fiber orientations, we often recommend just creating a bunch of dummy plies with a small increment small increment between the fibers of each of the plies, and then just do a size optimization, right? And then see which ply orientations yield you the largest size resulting from the optimization, largest thickness. Okay. So you got all that functionality in there as well. And if you'd like me to go into any more detail on any of those optimization or post-processing capabilities with composite structures with OptiStruct, just let me know. But with that out of the way, that just about covers everything that I couldn't quite get to during the live demo. So I hope this was helpful for all you guys.